Okay, so good afternoon, everyone. Welcome to the first live interactive session of the course Viscous Fluid Flow. The course code is ME66, and this course, as you all know, is being taught by Professor Amaris Dalal from IIT Guwahati. And I am Rajnandan. I am a PhD scholar from the discipline of Mechanical Engineering, IIT Gandhinagar. So I will be there for you in helping you to solve out certain problems associated with the contents that you get to receive every week. So the idea of this interactive session is not to just solve whatever the assignment problems that you are given verbatim, but to give you an idea of how to approach those problems. So needless to say, I will not be solving directly the problems that you get in the assignment. This is your job, and this is for you to figure out how to solve them. On the other hand, what I will try to do is I will help you to come out with some problems which are similar to the one that you receive every week. And then, based on those concepts that you learn every week, based on those concepts, you will, it might help you to go forward with your assignments. So this is basically the idea of the interactive sessions. And these sessions are recorded and will be uploaded on YouTube. So in case if you miss the sessions, you can easily get them in YouTube. The link of which will be, I think, it will be uploaded in the course website. So with this, let's get started. And also, just to tell you that the notes which I will be preparing and which I will be solving, these notes that I will be writing, and this will be provided in the course website as per communications with the PMRF office. So again, you can access them whenever you need in any point of time. So with this, let us get started in this session, in today's session. So what we will do is today we will, so our brief agenda is to discuss sums basically on two aspects. One, first we will revisit some fundamental definitions of fluid dynamics. I mean, revisit means revisit certain, we will revisit certain problems that are associated with these fundamental definitions involved in fluid dynamics, which I think you guys know. For instance, the stream function, the velocity potential function, the continuity equation, and so on and so forth. And also, we will try to solve certain problems associated with the very famous and infamous theorem, which is known as the Reynolds transport theorem, which is basically abbreviated in fluid mechanics or fluid dynamics as RTT, which I think is a part of your first week's assignment. So we will revisit certain examples and sums associated with the Reynolds transport theorem. Yeah, so these are basically the two agendas that we will try to follow. Uh, so we I will stop here for some time. If you have any doubt, you can ask me before proceeding with the problems. I'll maybe stop here for 1 or 2 minutes. If not, we will start. Meanwhile, I'll just check had I start my recording or not. Just 1 second. So recording is going on. Yeah, okay. ठीक है. All right, guys. If you have any questions, you can ask me regarding how these interactive sessions will go on, or any kinds of like. So one thing, and I would like to make clear is that you can stop me at any point of time whenever I am solving a problem. You can stop me, you can question me, you can ask me. Feel free to just unmute yourself, or like you can type in the chat box or whatever way you like. Uh, yeah, so this is basically how it goes. So if you don't have any questions, once again, for the ones who joined late, welcome to the first interactive session. We will basically, as I said, we'll basically be solving problems here. And today we will be solving problems associated with some basic definitions of fluid dynamics and the Reynolds transport theorem. So let's begin. So the first problem, as you can see, I think I think I am audible, and also my iPad screen is visible there. So as you can see, the first problem, so I just want to make sure that I'm audible or not. Can anybody just write in the chat box that I'm audible? Can uh, can anybody just help? Can just type if I'm audible or not. Okay, thank you. Yeah. Okay. Okay, thank you. So let's get started. So basically, we'll be solving a problem, which is basically again associated with the Reynolds transport theorem. So the problem goes something like this. It's a very simple problem, but a good problem for a start. So, so the problem goes something like this. So we are to evaluate, as you can see from my screen, we are to evaluate the change of water height for an inflowing tank. So the thing is, there is a tank, as you can see, and there are two pipes that is connected to this tank in this way. And water is being flowing inward to this tank, as you can see from the diagram. So the idea is that, and the objective is that, as you can see, when water flows inside this tank, the height of the water would inevitably rise, right? That is the basic thing that one can always think about it. So when water flows in, its height will rise, and of course, the height that the water rise at a certain level is obviously a function of time. So this h of t, which is basically the instantaneous height of water at any point on this reservoir, will inevitably be a function of time. So given this, what they are asking is that they want us to calculate what is this change of height with respect to time. So how does this h of t vary with respect to time? That's what they're asking. So I hope the problem is clear. The system dimensions are also given. For instance, the area of the tank is given to be 80. The total height of the tank is given as capital H, as you can see. The inlet, so this point is inlet 1. The inlet 1 velocity, of course, the velocity of water at inlet 1 is given as V1 with its area A1. And the velocity of water at inlet 2 is given to be V2 and A2, which precisely is the area. Here, I would like to, so I want you to first see the problem and try to think about it. How will you go on and approach this problem? So this is the first thing that you need to do. But before allowing me, you to think about this problem, I would like to highlight a certain aspect is that this V1 that you can see is V1. I would like to clarify the one thing is that this V1 is basically, so this is basically the average velocity at cross section A1. So the idea of this average velocity is that, so this particular bit of information is given to us. The idea is that in any cross section, the water velocity in principle doesn't remain constant, which we all know, because we know that this shape, so if water flows through a pipe, its velocity profile is always parabolic. So the idea here is that this V1 is not that parabolic velocity profile that is given to us. Instead, this v1 is basically the average velocity of those parabolic velocity profile that we see, and then this is average throughout the cross section. So in other words, this v1 will act as a constant for this problem. So this is something that you guys need to appreciate. Similar case and similar analogy can be drawn for v2 as well. So I would write here that this v2 is basically the average velocity at cross section 2, which in principle, so this v1 and v2 in principle are constant. That is something that I wish to say. Okay, so if this is clear, uh, let us think of how can we solve this problem. So the objective is to find this dh by dt, which is basically how the rate at which h of t, which is basically the instantaneous velocity of water at any position of the tank t, at any position of this tank changes with time. So this is something that we wish to find. Again, I would wait for some more time, for some time. I would wish for you guys to think about how we shall go on and approach this problem. And then I will proceed with the solution. And again, if you have any doubts, you can feel free to unmute yourself, or you can feel free to type in the chat. And yeah, so we shall start. So think about how to approach this. Okay, by the way, this rho W, as you can see, this I have not written it down here. I would clarify it here. So this rho W is basically the density of water. And this rho A, as you can see, this rho A is actually the density of air that is above this water. This rho A is basically the density of air that is above the water height inside the tank. So this rho A is density of air above the water height. All right. So with this information, let us now start to let us now try to solve this problem, how this goes. So the very first thing, as you can see in this problem, is the choice of a control volume. So what we will do is we will choose this this water portion inside the tank to be our control volume. We'll choose this as our control volume. Some of you might also choose this entire tank as a control volume. Okay, it is so in fluid mechanics, or typically when you are we're dealing with Eulerian approaches, we need to choose a control volume for moving forward, for going ahead to solve a problem. Now the choice of the control volume is always it's always with the one who is solving the problem. So it's our choice basically on what portion of the problem do we choose as a control volume. Now what to choose and what not to choose is again it's a case of expertise. But here in this case, if you also choose this entire tank to be our control volume, you will end up getting the same answer, so as to as choosing this this water portion as a control volume. So I will begin by solving. I'll begin by solving this problem. I'll begin this problem by choosing this water portion as my control volume, and later on, I will not do that by myself, but you can also try by choosing the entire tank to be the control volume and then going ahead to find how this dH by dt changes with time. Okay, so now I will choose this water portion in as a control volume, and then I will apply something which is called the Reynolds transport theorem in the control volume. So what? One second. One second. One second. So, okay. So what I will now do is I will apply RTT, which is the Reynolds transport theorem, and we will apply RTT for conservation of mass, of course, because the idea is to find out how this HT changes with time. So we'll apply RTT for mass conservation in the control volume. So let's now try to understand how do we apply RTT in this case. So this happens to be our control volume of the problem. So there is this part where the water comes in, and this part also where water comes inside the CV. So if you remember, the Reynolds transport theorem goes on something like this. So if I want you to recall, I think you have also learned this in the theory classes. The Reynolds transport theorem is basically a bridge, or it's a connection between a control mass system and a control volume system. Or in other words, if I have a property which I want to evaluate in a control mass system, however, I also wish to evaluate that same property in a control volume system. So the bridge or the connection which does this thing is known as the Reynolds transport theorem. Or Reynolds transport theorem is also a connection between a Lagrangian approach and an Eulerian approach. And I hope you guys know what is a Lagrangian and an Eulerian approach. But for in order to recapitulate what we have learned, I write by starting the Reynolds transport theorem for any general property n, which says that the rate at which this property n changes with respect to time in a control mass system, I will write a control mass system as CMS. So this CMS means it's a control mass system. This is equal to the rate at which the property per unit mass, which on we will denote is as eta. So I will explain to you what eta is. So this term denotes that the rate at which the property per unit mass changes inside the control volume plus the net efflux. So the net efflux term is denoted by area, it's a surface area integral of this term basically. So as you can see, one second, there has to be a row here. Sorry for that. Oh, no, there has to be an eta that has to go with it. Yeah, okay. So what this term changes, so as I said, so this is precisely the Reynolds transport theorem, as you can see. So this term on the left hand side denotes the change of the property in a control mass system, and the term on the right hand side is related to how the property changes inside a control volume. So this term is basically the rate of change inside the CV mean denoting the control volume, and this term is basically the efflux. Okay, so as you can see, this part comes from the Lagrangian description of the problem, while the term on the right hand side is basically the Eulerian approach. So the Eulerian approach doesn't, as you all know, the Eulerian approach doesn't focus on a single particle. Instead, it focuses on a particular region in space, and in that particular region, we try to evaluate how a property changes with time and the net efflux, which is basically the which is basically the property how it enters the surface and the difference between how it leaves the surface. So this is known as the efflux term in the Reynolds transport theorem. So for mass conservation, as you all know, this n becomes equal to m, which is basically the mass, and eta, as you can see, is basically the property per unit mass. So this becomes m by m, and that's why it becomes equals to 1. So the Reynolds transport theorem, in case of when we apply it for a mass conservation case, simplifies to dm by dt, because n becomes equals to m in a control mass system, and this is equal to, so eta becomes equals to 1, so this becomes equals to 1. So this is basically what del t integral over the control volume. By the way, this v, this basically denotes the volume integral, and this means I'm integrating the entire thing. I'm integrating rho eta over the entire volume, and this dv is basically the elemental volume that I'm considering. The reason why I put a mark here is that in order to distinguish the term with velocity. So since I'm denoting velocity as v, that's why I'll denote volume in this fashion. So this term simplifies to rho times dv. Okay, plus this becomes control surface integral of CS, means it's an integration over the control surface. It becomes rho v dot n cap dA. So this is basically the Reynolds transport theorem if we are applying it for a mass conservation. So this is something that I think you guys have also done it, but anyway, it's a good way of recapitulating things when you are solving a problem. So now try to understand one thing, that in a control mass system, mass is always conserved. That is this m, this cannot change with time, which means always remember that this dm by dt term in a control mass system will always go to 0, which means that this term will just be 0. And I'm assuming one thing, I'm assuming that this rho is basically constant, So I'm assuming this rho to be equal to constant. Assume rho to be constant. So then what I can do is, so this term goes to 0, this term goes to 0. So this becomes, so if I simplify the above expression, this will turn out to be rho times del t of integral over v dv plus rho integral over the control surface v dot n cap dA. And by the way, I forgot to mention one thing, that this n cap that you see is basically the unit normal. So if I, so in this cross section, if I, so this cross section in 3D would look basically something like this, this control volume in 3D. So n cap is basically, if I take a elemental area in this space, then n cap is the unit normal to this elemental area. So I think you are aware of what this n cap is. So that should not be a problem. Okay, so now let's simplify this. So this becomes rho. This control surface in control volume integral of dv, this, as you can see, this should anyway be so so what does this term mean? It means that I'm taking an elemental volume dv and I'm integrating this dv over the entire volume, which is nothing but the volume of the system or the control volume that I'm considering. So this becomes the area of the tank. So this becomes the area of the tank times h of t. So I hope the step from here to here is clear. I will again repeat. So the thing is, I am taking an elemental volume in space, let's say, and so there is a total volume in space, and I'm taking an elemental volume in this total volume, and I'm integrating this over the entire volume dv, which means this is nothing but the volume of the control volume that I am considering. So that's why this becomes so in our case, the volume of the control volume is nothing but the area multiplied by height. So I hope this is clear, and that's why this became AT times h of t. Okay. Plus, let us now try to evaluate the efflux term. Okay. So this becomes a rho. So the first case or the first inlet is basically this one. So as you can see here, the direction of the velocity vector is pointing inward inside the control volume, while the n cap, as you can see, so what I mean to say is the direction of the velocity vector is in this direction, while the n cap, that is the normal vector, or it's a normal unit vector, that is that no, it's, so n cap is basically the normal vector, which is a normal vector of an elemental area of the control volume. And in this case, as you can see, the n cap is basically in the opposite direction, which means that n cap is in this direction, right? So that's why for the inlet 1, this control surface integral of v dot n cap would turn out to be minus v1 times a1. Again, I would repeat why this became a minus here. The sole reason is, since the velocity vector is in the inward direction, or if I put a general coordinate system here, let's say this coordinate is x and this coordinate is y. What I mean to say is v is in the positive x direction, while this n cap, which is basically the unit normal outward of the elemental area, is basically in the minus x direction. And that's why if I try to calculate this term, which is basically this term v dot n cap dA for the cross section 1, it comes out to be minus v1 a1. I hope this is clear why it became minus v1 a1. And similarly, if we do the same exercise for this inlet 2, now as you can see, similarly the velocity vector, as you can see, is in this direction, and the normal vector is in the outward direction. Since the fluid is coming this side, but the normal vector of this elemental area will always face in the outward direction, and that's why for inlet 2 as well, this would be what? This would be minus v2a2. So I will stop here. If anyone has a doubt from this step to this step, how do we write that? And this is basically the main essence of this Reynolds transport theorem, how to use this Reynolds transport theorem in solving out problems similar to this, is to choose a control volume, then try to see what these terms eventually come out inside a control volume. And if you have a doubt from this step to this step, like I would stop here for let's say 1 minute. If you have a doubt, you can ask me, and then we'll proceed to calculate this h of t. Okay, so I hope if you don't have a doubt, that's very well. So what we will do is, since the area of the tank is so the area of the tank, it doesn't change with time, right? This means that this at it's a known and a fixed quantity. So since at is known and fixed, what we will do is we will bring this at out of this differentiation, and this h of t, is just a function of time, right? H of t cannot be a function of space because the height will only increase with time, right? Which means that this partial differentiation can be now written as an ordinary differential equation, or it can be now written as an ordinary differential. That's what I mean to say. So since at is known and fixed, and h of t, so this is just a function of t only. So this is how we denote a function. I hope you guys are familiar with these things. So since at is known and fixed, and the height is just a function of t only, I can write this term as it's rho at times dh, which is now just a function of time, by dt. And the other side would just simplify to be rho times v1 a1 minus v2 a2. Where this a1 and a2, I repeat, this a1 and a2 are known, as well as this v1 and v2 are also known. There has to be a row here. Okay. So the idea is we need to find this dh dt. If you remember, how does this h of t changes with respect to time? This is something that we need to find out. So I will take the other terms in the other side, and then what you shall get is, you get something like this: rho at dh by dt. This becomes equals to rho times v1 a1 plus rho times v2 a2, and then you can cancel this. You can cancel these rows from both the sides. If you do so, you end up getting this dh dt, which we seek to find out as v1 a1 plus v2 a2 divided by the area of the tank. Where this is the answer that we are looking for. This is basically the answer that we are looking for, where you can see that all these quantities are known to us. See, this v1 is basically the average velocity of the water at inlet 1, which is coming inward, and this v2 is basically the average velocity of water coming inward in cross section 2. a1 a2 are their respective areas, which is basically a measurable quantity, and at is the area of the tank, again something that we can measure. So this means if all these quantities are known, simply by applying RTT, you can find out in a tank how this water height changes with time. So this is the objective of the first exercise. I hope this is clear to you. Uh, I'll wait here for some time. So if you have any question or suggestion on this problem, you can feel free to bring it forward. So this is something that we did. I would repeat what exactly we did, such that we are on the same page. So we had a tank, and then we had some waters coming in. We had a pipe which carries water, which comes inside the. So through the pipe, it comes inside the tank. There were two cross sections, 1 and 2. So we seek to find out how this height, water height, actually changes with time. So the objective is again to find this dh dt. So we applied the much celebrated Reynolds transport theorem for mass conservation, evaluated the individual terms, that is the volumetric term and the efflux term, for the for the Eulerian part, and for the Lagrangian part, that is this part. We said that mass cannot be destroyed in a system, in fluid dynamics at least. So we said that the rate of change of mass inside the control mass system would just cease out to be 0, And then we calculated how this, so we calculated the efflux term. We heavily discussed like how this became minus and all this, how from where the minus sign came, and that is very important. Uh, Again, this minus sign is so the plus or a minus sign again depends on our choice of the control volume as well, which is something that you must take care. And then we evaluated how this dHdt expression would look like, and this basically came out something like this. So this is the first problem that we did. It's a relatively simpler problem, but it gives us a flavor of again applying how to use the Reynolds transport theorem in such practical cases. Okay, so if this is clear, I would move to the next problem. Yeah, before proceeding to the next problem, I would like to put forward a question which you can answer in the next class, or you can answer it in answer yourself as well. Is that, can you repeat this problem now? Can you repeat the same problem by considering this entire tank to be as a control volume instead of considering this water part inside the tank to be the control volume which is solved for? So the question that I'm putting forward is that if you now consider this both the water and the air part inside your control volume, do the calculation by yourself, and you can see that eventually this dHdt would come out to be of the same expression. Because see, the choice of a control volume is up to us. We can choose whatever control volume we wish to find. But the rate of change of water height, that should not be a function of your choice of the control volume. That's an universal case, right? Ki if there is water flowing inside the tank, the rate at which that water would rise or would fall is just a function of some physical quantities like this V1A1, V2A2, and it should not be a function of your choice of the control volume. So whatever the control volume you choose, these dHdTs that we calculate, which is this V1A1 plus V2A2 divided by AT, this answer would inevitably be the same. So you can do this exercise at your place, and then you can verify that this is indeed true. If you have any doubts, you can ask me, or you can put your doubts in the discussion forum of this course, and we will try to address it. So let's now start the second problem or on Reynolds transport theorem. So this is basically this is more of an applied problem, uh, which I say is, so it's something known as the jet impingement on a moving plate. So the idea of this problem is that I'll describe you the physical paradigm of this problem. So the idea is that there is a plate which is attached to some wheels, which means that this plate can move in, let's say, the x direction at least. And from a nozzle, as you can see, there is a jet that is coming out. So this jet, you can consider it as a jet of water, which is coming out with some velocity. The velocity Vj, which is the velocity of the jet, is given, and this jet hits the plate. So since as you can see, this plate also moves with some velocity Vc, which is basically 15 meter per second, 15 meter per second, as you can see. So since the jet comes out with a velocity higher than the cart or the plate velocity, this means that the water jet would now hit the plate. So what I mean to say is since Vc is less than Vj, this means that the relative velocity, based on the relative velocity concept, the water would now hit the plate. The idea is that, or the objective is that, if the water hits the plate, I mean the water coming from this nozzle hits the plate, what is the force that this plate experience on this impact? Okay, so I hope the question is clear. So this means if this jet which possesses a velocity Vj and an area Aj hits the plate, which in fact this plate in turn is moving with some velocity 15 meter per second, then what actually is the force that this jet exerts on this plate? This is something that we seek to find. Okay, I think this is clear. So I hope the question is clear to you. So again, if you if you like think a little bit about it, we shall be using the Reynolds transport theorem only. It's a similar kind of problem, but here, since it comes, so you can understand that since we need to evaluate the force, we must first use Reynolds transport theorem. We must first use Reynolds transport theorem for conservation of mass. Okay, and then we'll extend the Reynolds transport theorem for the conservation of momentum as well. We'll use conservation of momentum. So conservation of momentum will give us, so if we use Reynolds transport theorem for conservation of momentum, it will eventually give us the force, because RTT, if we apply it from a controlled mass system for conservation of momentum, it just becomes the Newton's second law. Because Newton's second law, so the laws of nature, or in fact, to be more precise, the Newton's second law, all these things are designed for a controlled mass system. And then we'll connecting this Newton's second law designed for a control mass system with the control volume in order to evaluate the force that the water jet exerts on the plate. So I think the idea on how to solve this problem is somewhat clear. We will stop. Maybe I'll stop for 1 minute. You can think about this problem. You can think about how you will go ahead to try and solve this problem. And then I will solve it for you. All right. Let's let's now try to solve this problem. Again, the first step in applying Reynolds transport theorem, as I have repeatedly mentioned, is the choice of a control volume. And now, what we will do is we will choose a control volume. So what we will do is we will choose a control volume which is attached to this plate. This means in the earlier case, when we solve for this water entering a tank, we choose the control volume as the water portion inside the tank. Here what we will do is we will choose the control volume to be this plate uh, which is moving with some velocity vc as a part of the problem, and then we will do the analysis on this chosen control volume. Needless to say, this control volume now, since this is attached to the plate, which means this control volume will move with respect to a fixed axis, let's say this red axis. So, or in other words, if I sit on this control volume, then a person sitting on this axis will see me moving with a velocity vc. I think this is common sense to everyone. So we will start this first by uh, describing the choice of the control volume. So the control volume here, the CV, what we will do is, so this CV is basically attached to the plate or cart, whatever you say, it's plate or cart. This is the first thing. Now, we will now apply RTT, which is the Reynolds transport theorem for mass conservation, of course. So if I now apply RTT, so we'll apply RTT in this control volume for mass conservation, then I will now write directly. So the RTT says that the rate of change of mass with respect to time for a control mass system is equal to the rate at which the property changes inside the control volume, which is this term, plus the efflux, which is basically something like this. Okay, as I said, this term will always go to 0 since mass cannot change inside the control volume. In this case, this term, that is control surface integral of rho dv, we can see that this term would also boils down to 0. The reason behind is that the volume of this control volume will not be a function of time. In the earlier case, the water level was continuously rising. So this means that the height would change with time, and this means that the control volume, that is the water volume that they considered, that would basically change with time since the height was rising. But in this case, the control volume of the cart, or so the control volume that is moving with the cart, this will not just change with time, right? Because this would remain stationary, which means that this term in this case would go out to be 0. So we end up inevitably, we just end up to be, in this case we just end up something like this. So it's control surface integral of rho v dot n cap dA, which becomes equals to 0. So now let's evaluate. So we just end up with the efflux term. That's the second way of telling, that's the second implication of applying mass conservation in this control volume. I hope this is clear to everyone why these two terms became 0. So now if we try to evaluate this efflux term, so first we need to, so evaluating efflux means we need to examine through which cross sections the water is coming and leaving. So let's do this for this case. So in this cross section, through this cross section, I would name it as cross section J, or I would name it as cross section A. The water is coming inside the control volume in this direction. Okay, and through these two cross sections, through this and through this, okay, I would name it as cross section 1 and cross section 2. Water is just bifurcating and going out of it. So it's coming to a cross section. So it's coming to a cross section A. It gets bifurcated and it just moves out to cross sections 1 and 2. So I hope this is clear. Uh, so so the efflux. So the idea of evaluating the efflux term based on the choice of the control volume should be clear to everybody. And now if we evaluate this, if we just evaluate this term, so if we apply this for, this bit needs to be applied to all the individual areas through which there is an efflux in the control volume. So if we evaluate this for this area A, this term would just be, so as you can see, the velocity is in this direction, the unit normal vector is in the opposite direction, which means this would turn out to be minus rho, the velocity of water at cross section A. I would name it as VA. Okay, and we will find out what VA is. And then this becomes AJ, which is basically the velocity of jet. Because the velocity of water in this cross section is nothing but is associated with the area of the jet, which is AJ, which is given to us. And this VA, so this VA is nothing but, so this is the velocity of water at that cross section AJ, and since the control volume itself is moving with the cart, this means that VA would nothing be the velocity of jet minus the velocity of the cart or the velocity of the plate, whatever you say. So I think this is clear to you how VA becomes VJ minus VC. VA is just not equal to VJ, or it is just not equal to VC solely because now the control volume itself is moving with the cart. So it's just the relative velocity between the VG and VC, VG and VC, VJ and VC. Okay, so I hope this is clear. And then if we apply for, so this is for the cross section A. So we are done with cross section A. Now if we apply for cross section 1 and cross section 2, see, for cross section 1, the velocity is in this direction and the unit normal is also in the same direction. And similar analogy can be drawn for cross section 2, which means for cross section 1, this term would be plus rho V1 A1, and for cross section 2, it would be rho V2 A2, and this is equals to 0. So I hope this expression that we wrote here uh, can be understood by everybody. Okay, so I hope this is clear to you. So from this term we evaluate this term. Before proceeding, I would again stop here for some time. If you have any doubts, you can ask me. Again, I would repeat why this VA becomes equal to VG minus VC is because since this control volume itself is moving forward with the cart, so the velocity of water, at cross section A for this control volume would just be VG minus VJ minus VC. Okay, and these terms are obvious. I don't think so you need to think more about this term. However, this bit is important to us. So if we simplify this now, so let's simplify this. So it becomes rho times Vj minus Vc plus rho times V1 A1 plus rho times V2 A2. This becomes equal to 0. Okay. And then this rho's, since density of water is considered to be constant, these rho's would cancel each other. And what we will get is we will get okay, this there has to be an Aj multiplied by this. So what we shall get is we get something like Vj minus Vc multiplied by this Aj. Okay, this becomes equal to V1 A1 plus V2 A2. Okay, now here lies an important part. So from here to here, from here to here, this is just math, and I hope you can follow. But now let's try to understand one thing. We know we know the value of Aj, we know what is Vj and Vc, but we do not know what is A1 and A2. This is not given to us. See, this jet comes, so what happens in this problem? This jet comes, it gets bifurcated in these two directions, and it just moves out in the y direction, which means even though we don't know what is A1 and A2, from the symmetry of the problem, we can write that. So what I mean to say is that from symmetry, we can write that this A1 will be equals to A2 and that will be equals to Aj by 2. So this is solely due to the symmetry of the problem. Okay, since we don't know what is A1 and A2. And then if we just substitute this, here, what we will get is we'll get Vj minus Vc times Aj, and this becomes P1 times Aj by 2 plus V2 times Aj by 2. This Aj's would now be cancelled, and we end up getting V1 plus V2, that is equal to 2 times of, we get V1 plus V2, okay, that is equal to 2 times of Aj Vj minus Vc. Okay, I think this is okay. Please check the algebra. If I am wrong, like please point me out. So I hope it's clear for everyone till this step. Okay, now try to understand one thing. Since I have said that A1 is equals to Aj and this also becomes equals to A2, which means that A1 and A2 are also equal. This means that if these areas are also equal, that is the cross-sectional area of A1, that is the cross-sectional area A1 and the cross-sectional area A2 are equal. That means from mass conservation, I can also conclude that V1 should be equals to V2. Since I have considered A1 to be equals to A2. And this is again because I can always write for cross section 1 and 2, I can always write rho times V1 A1 equals to rho times V2 A2. And this is only because I have assumed that density, so this comes from mass conservation. This comes from mass conservation. Okay. So since I've assumed that the density of water is fixed and it is not varying, so I'm considering water to be an incompressible fluid, which means that rho is constant, then I can always write the mass conservation the mass conservation for this 1 and 2 as rho times v1 a1 equals to rho times v2 a2. And since I have said that a1 is equals to a2 by symmetry of the problem, this means that v1 has to be equals to v2, and that's what we have written here. Okay, so if we do this, what we get is we can write 2 times of v1, since v1 is equals to v2, is equal to 2 times of vj minus vc. And then what we get is we get v1 as just vj minus vc. And I think this becomes 5 meter per second. Okay, so this is one part of the problem that we solve. So I hope this is clear by applying mass conservation. Okay, so I hope this is clear to you. Since Vj is 20 and Vc is 15. So Vj minus Vc is just 5 meter per second, as you can see from this step. So we are not done yet, by the way. We need to also evaluate what is the force that the water jet exerts on the moving card. And for that, let us now apply, in order to evaluate the force, I would write to evaluate force. Uh, so in order to evaluate the force, we need now to apply RTT. Uh, RTT means the Reynolds transport theorem for momentum conservation. Now, I'll write down here to evaluate force. We apply RTT for momentum conservation. Okay. So let's now try to apply RTT for momentum conservation in the same control volume that we saw. So the control volume that we took is this, basically is this control volume. So now if I apply momentum conservation, but here is one important thing that I would like to point out is that unlike mass conservation, momentum is basically a vector. Okay, so momentum is basically mv, and v, since velocity is a vector, so momentum itself is a vector, which means that if I now apply RTT for momentum conservation, I have to apply it vectorically. Or in the other way around, if I want to apply RTT for momentum conservation, I need to apply in some specific direction. Let's say if I want to apply in x direction, I have to write RTT for momentum conservation in the x direction, because since momentum itself is a vector quantity. So first what we will do is, either we can apply it vectorically, or we will specify the direction and then apply RTT in the individual directions. I hope this is clear to everyone, since momentum is basically a vector quantity. So what we will do is, we apply RTT for momentum conservation. First we will apply it in the x direction. We apply RTT for momentum conservation in x direction, let's say. So if we apply RTT in x direction for momentum conservation, so let's now try to apply it. So the property now becomes momentum, and since we are applying it in x direction, it becomes px, which is basically the momentum of the fluid in the x direction. This eta, this is basically the property per unit mass, and since property is momentum, which is basically px, divided by, so this becomes eta x, which is basically px by mass. This becomes equals to the velocity vx, since px is vx times the mass, and mass get cancelled. Okay. So now if I apply RTT, so now applying RTT, so what I get is, for the left hand side, it becomes ddt of px, which says the rate of change of momentum inside the control volume, and this basically can be written as del t. For the right hand side, this can be written as del t integral over the control volume rho times the velocity vx, which, since eta becomes equals to vx, so this would be vx times this v dot n cap. Oops, I'm sorry, this v dot n cap won't come here. So it is rho v. Okay, so this becomes rho v dv. This is for the volume term. And for the efflux term, this becomes integral over the control surface. It becomes rho vx v dot n cap times d. I hope this is clear to everybody. How did we apply RTT for momentum conservation in the x direction? So if it's not, kindly speak out or kindly write in chat, and I'll obviously address the doubts if there arises any. So try to understand. I hope that is to this point everyone is clear and we are on the same page. So try to understand that this part is from the control mass system. This part that we write here, this is from the control volume analysis. And if I now apply Newton's law, I said that Newton's law and the laws of nature basically are so they are designed for control mass analysis, which means that this dpx by dt, by using Newton's second law. So if we apply Newton's second law, which says that, so Newton's second law says what? It says that the rate of change of momentum is just the force, and we seek to investigate the force in the x direction, which means if I now use second law, that is from Newton's second law, I can write is what I can write is that the force in x direction is basically equals to the rate of change of momentum. Okay, and this rate of change of momentum can be equated to this part in the control volume by using the RTT. And that's why, so you can see here how beautifully there is a bridge between the laws of nature and the one that we seek to evaluate for a control volume analysis. So this becomes equal to, so this is by using second law, this becomes equal to del T for the control volume, okay, rho Vx dV plus this way, integral over the control surface, rho Vx v dot n cap dA. So again, I would repeat, this thing comes from the Reynolds transport theorem, and the equality of this and this comes from the Newton's second law. So this basically deals with a control mass system, and this equal to comes from the RTT, and this connects, this RTT connects with this control volume analysis that we did. So indirectly, now I can write, so what now I can write is that based on the above expression, I can write that the force in x direction is nothing but del T integrated over the control volume, which I will denote it at Cv, times rho Vx plus this term v dot n cap dA. Okay. So now, as you can see, this term would be 0. Why? So this is because, again, the control volume, the cart control volume doesn't change with time, which means that this term would be 0. So the force in x direction, would just be control surface integral of rho Vx times v dot n cap dA. Okay. So similarly, as you can see, now we just need to evaluate this v dot n cap. So the v dot n cap, as you can see from, so we already evaluated it. The v dot n cap is basically this. So it is basically associated with this area, and this would simplify to be nothing but Vj minus Vc, as we already evaluated. So this would nothing be minus rho, and Vx would also be equal to Vj minus Vc, because Vx is nothing but the velocity of water at cross section A, right? Because we need to evaluate this control surface integral at cross section A, which is the inlet of the water. So this becomes minus because the n cap and the velocity is in the opposite direction, and it becomes Vj minus Vc whole square times Aj. I hope this is clear to everybody. How did I write this thing from this thing? I would explain once again if you have a doubt. So Vx basically is what? Vx is nothing but Vj minus Vc. Why? Because I need to evaluate the velocity of water by choosing a control volume which is moving with the cart at cross section A. That's why it becomes Vj minus Vc. And this v dot n cap, is nothing but minus Vj minus Vc. Why? Since this n cap and the velocity is in the opposite direction. Velocity vector is in the opposite direction, and that's why the multiplication of these two becomes Vj minus Vc squared with a negative sign, which means now the force Fx is basically minus, so what, rho is 1000, we all know density of water. Vj minus Vc, I think, so Vj minus Vc is 5, so this becomes 5 squared times area of jet area. So I think jet area is given to us. So what is jet area? Jet area is 3 centimeter squared. So this becomes what? This becomes, so it's 3 centimeter squared. So it becomes 3 into 10 to the power minus 4. Okay. This becomes 3 square into 10 to the power minus 4. And whatever, so whatever is this multiplication is nothing but the force in Newton that is being exerted. So this is the force in Newton that is being exerted by the control volume on the water, since we consider the control volume to be the chart, which means, so this is the answer anyway. However, if we look at the other way around, that what is the force So if we look at if we look the other way around, that what is the force that the water exerts on the control volume is nothing but a negative of this fx, which is nothing but the positive sign, which is the basically 1000 into 5 square into 3 square into 10 to the power minus 4. So I hope this is clear. Uh, how the force is being calculated. I would repeat once again. This minus sign came because we considered the control volume to be on the chart. So this control volume, this is the force that the control volume exerts on the water. So by Newton's third law, the other way around, the force that the water exerts will be negative of this force, and this will be in the positive x direction. That's what this analysis says to us. Uh, I hope this is clear. However, the magnitude of the force would just be this bit, as you can see here, as you can see from this expression. I hope this is clear to everyone. How did we calculate this force? And I hope this problem is clear. So ultimately, we need to determine what is the force on the card. And one more thing, if you minutely observed, we applied Reynolds transport theorem for momentum conservation in the x direction, but we didn't apply this for the y direction. And I said that the net force would just be that. So the reason behind this thing is that, so I think you should have thought about it, or you should have pointed me out that why didn't we apply RTT for momentum conservation in the y direction. The simple reason for this is that in y direction, as you can see, in y direction, which is basically this direction, the problem is inherently symmetric, which means that there can't be any force that the system applies on this control volume in the y direction, because this v1 it becomes equals to this v1 becomes equal to this v2, which means that a1 is also equals to a2. So if we apply RTT, we will see that this will anyway goes to 0. What you can do is you can apply RTT. What I would suggest you to do is you go on and apply RTT in the y direction, and you can say for yourself that the net force in y direction would just turn out to be 0. That's the most simple thing. Okay. Since v1, the velocity that is going in the plus y direction is equal to the velocity that is going in the minus y direction, and since v1 factorically v1 is minus of v2, this means that there won't be any force in the y direction. That is simply due to the symmetry of the problem. Anyway, you can apply RTT and try to prove yourself that this exactly is the case. Okay. All right. We are done with second problem. This of course this problem is a little involving problem. I would wait here for some time. Okay, I'd wait here for some time. If you want to take notes, or what, if you want to write by yourself, you can write, and then we will proceed with the next problem. If, in the meantime, if you have any doubts, you can speak, or you can write in chat, and we will then move in the next problem of our interest. So you can work this sum. You can basically work this sum, and you can evaluate what is the net force that is being exerted in Newton, of course. So I hope the other two problems are clear to you. Okay, so if you don't have any doubts, we will move ahead with the third problem. This is relatively a simple problem. which is associated with the stream function, of course. And the what the question is asking us that they wants us to evaluate the stream function for a given flow field. So the velocity field is given, which is basically, so the x component of velocity field is ax ex. Ex is the unit vector in the x direction. The y component is of course minus ay ui, where a is just a constant bearing a magnitude of 0.3 second inverse. Okay, so the velocity field is given, and as you can see this velocity field, can you tell me that is so? Can you tell me whether this velocity field is in the Eulerian or a Lagrangian description? Uh, but just by looking at the velocity field. So so my question is, can you tell me whether, so this velocity field is given? So my question is, before evaluating the stream function, can you tell me whether this velocity field is in the Lagrangian description or an Eulerian description? Uh, So you just need to see, so you just need to think about what basically is a Lagrangian description is, or and what basically is an Eulerian description is. And okay, so see the velocity component, as you can see, the velocity component u, let's say in the x direction is what? It is just ax, right? So what basic, and of course the velocity component in y direction, v, is nothing but minus ay, as you can see from here. So see, so in Lagrangian description, what we do is we don't focus on a space or a region. Okay, what we do is we try to track individual particles and try to see the motion of those particles. Hence, in Lagrangian description, there cannot be space dependence of any property. Okay, it has to be only time dependence. So we will solving one more problem where we'll be clear what basically distinguishes a Lagrangian problem and an Eulerian problem. But in Lagrangian problem, so the properties will just be a function of time because we track only one particular particle and then try to see how this particle basically moves with time. However, in Eulerian approach, instead of tracking a particle, we try to fix the region in space, and then in that region we try to see how the property changes. So since we are fixing regions in Eulerian description, there has to be functions of spaces. Functions of spaces means functions of coordinates like x, y, z, r, theta, phi, or something like this. So since these velocity, so these properties, that is these velocity components, are a function of the space x and y, this means this has to be a Eulerian description. Okay, so I hope this is clear. Uh, Whether this is a Lagrangian or an Eulerian description. So if this is clear, we now move ahead. We now go ahead and try to evaluate the stream function. So remember from the definition of stream function, so from the definition of stream function, we know that the x component of velocity is related to the stream function as just del psi by del y, where psi is nothing but the stream function. So this is from the definition. It's from definition. Okay, and we know that this u is given as a times x, which means ax is just del psi by del y. And now what we need to do is this del psi becomes equals to ax times del y. So now what we need to do is we need to integrate this, and we need to integrate this with respect to y, since there is this del y here. So this becomes psi, which may be a function of x and y, and this becomes axy because we are integrating this with respect to y. And since we are integrating this with respect to y, there has to be an f of x here, which is some arbitrary function of x. So this is the rule of how we do partial integration. And now this psi becomes axy plus f of x. Okay. So, however, this is not enough. Although we require to find the stream function psi as a function of x and y, this is not enough because we don't know what is this f of x. And in order to evaluate this f of x, we will use the other bit of information, which is the v component of velocity, which is basically this. So, this v is nothing but, from the definition of stream function again, this v is nothing but del psi by del x. This is from what? This is from the definition of stream function. Okay, so this V, so if you now evaluate, so from this, if you now evaluate del psi by del x, so what we would get? We would get minus a times y minus df of x by dx. Okay, so let's put it as number 2. So what we did is we just evaluated this term del psi by del x, and this becomes df of x by dx because this f of x is solely a function of x only. Now what we'll do is we already know, so we know that this v, which is the v component of velocity, is nothing but, so it's nothing but minus a times y. Okay, this is given to us. This v is nothing but minus a times y. So just name this as 2a, and then very carefully, if we see this v, from here we got v equal to minus ay times df of x by dx, and from the question itself we know that v is just minus ay. So if we compare this and this, so if we compare these two, that if we compare if we compare 2 and 2a, what we would get is we would get df of x by dx has to be equals to 0. Okay, which means that f of x will just be some constant, and we'll name this constant as some c. So now we evaluated this f of x, which we actually seek to evaluate for. Okay, so therefore the stream functions that we evaluated, which is this, the stream functions that we evaluated will now look like psi, which is basically a function of x and y, is nothing but, so what is it? So it is a times xy plus f of x, and this f of x is a constant. Okay, so that's it. That's the stream function that we tried to evaluate. Now note that, can you tell me what will be the nature of this? So what will be the shape of this stream function? So if you uh, if if you can observe something from here, can you tell me what is the nature of this stream function? So if we draw the stream function in, let's say I now draw this stream function in 2D Cartesian space. Let's say this is y and this is x. So ax plus, so when c becomes equals to 0, let's say psi just becomes equal to xy with some constant, which means this is the form of a rectangular hyperbola. Okay, so these streamlines, so there will be now, since this c is just an arbitrary constant, there will now be a family of streamlines. Okay, which will now look something like this. So this will be one streamline for some c1, this would be another streamline for c2, and this would be the third streamline for c3, and so on and so forth. Okay, so you can draw the streamline something like this. So I hope this is clear how these streamlines look. Uh, so this, yeah, so that's the question that is, so the question is asking up to here. Okay, but we were also went ahead and draw how the streamline should look like. Okay. All right. So I hope this is clear. I would again wait here for some time. This was a more simpler problem. But before ending this problem, I would like to highlight one more thing, that see, when we define streamline, so this is just a note. So when we define streamline, we say that the streamline satisfies this definition, that u, that is the x component of velocity, is just del psi by del y, and the y component of velocity is just minus del psi by del x. So when we define streamline using this means that, so the idea is that if we are defining streamline, so what I meant to say is that if we are defining a stream function, so if we are defining a stream function which have some multiple streamlines, let's say we are denoting the stream function as psi. Okay, then continuity, what I mean to say is that continuity, at least the incompressible continuity, is trivially satisfied. So this is a very powerful statement, because in anywhere in anywhere where you are defining stream function with something like this, you don't need to care about whether it satisfies continuity or not in any coordinate system. Because if a law is, or if it's, so if you can prove that continuity is satisfied in Cartesian coordinate system, then it will also be satisfied in spherical coordinate system or cylindrical coordinate system or something like this. So the idea is that if we are defining a stream function, you don't need to bother about the continuity equation, because continuity equation will be trivially satisfied. You can actually prove that, and I will show you how you can prove that. It's a very simple proof. So the proof for this is that, so the proof for this is that, so what is the continuity equation? Can you tell me what is the continuity equation for incompressible flows? So if you remember in Cartesian coordinate, so irrespective of the coordinate system, the continuity equation for incompressible flow is just divergence of velocity field equals to 0. That is very simple. Okay. So if it's incompressible, the continuity equation says that the divergence of this velocity field should be equal to 0, which means if you write it in Cartesian coordinate system, it means that del u by del x plus del, let's say, del u by del y, this becomes equals to 0. Okay. Let's say we are considering a planar geometry where there is no, oops, this has to be v. So del u by del x plus del v by del y has to be equals to 0. So this is from, so this is written for a 2D planar xy system. Okay. Now let us introduce the definition of the stream function. So for the left hand side of, this expression or equation, if we now insert the definition of stream function, I said that u is nothing but del psi by del y, and v is nothing but minus del psi by del x. Okay. So using this, let us evaluate the left hand side of this thing. Let us go on and evaluate this. Okay. So del u del x becomes, so if you, so this becomes, so the left hand side becomes del x. So u is nothing but del psi by del y, which is basically this, and plus this becomes del y, and v is nothing but minus del psi by del x. Okay. So this term simplifies to del square psi by del x del y minus del square psi by del y del x. And if psi has a continuous second derivative, then you can interchange this term, then you can interchange del y del x as just del square psi by del x del y minus del square psi by del x del y, and this is nothing but equals to 0, which is basically the right hand side. Okay. This means that if we are defining the very definition of a stream function, if we are defining stream function in this way, okay, it inevitably, or it will always satisfy the continuity equation. So that's the idea what I wish to what I wish to tell you through this problem. I hope this is clear. Okay. So again, I'll stop here for some time, and maybe we'll go to the next problem. Okay, so if you have any doubt, you can ask me, or we'll proceed to the next problem of our interest. So if you have any doubt, you can ask, or you can read the next problem on your own. Maybe something, yeah. Okay. So you can maybe read it something like this. Okay. You can read this problem. I'll give you some time to think about it. This is a very important problem, and it clarifies our concepts on Lagrangian and Eulerian description. So I named this problem as particle acceleration in Lagrangian and Eulerian description, but It basically is nothing but some fundamental definitions only. So you can read this problem on your own and then try to think about how to like solve this problem. And I'll give you maybe some time to think about this. All right. I hope you have at least went through this problem. So so as you can see, this problem says that so this is basically evaluating the particle acceleration in Eulerian Lagrangian description. So what this problem says is that so there is a duct kind of shape which is basically converging in nature, and the center line velocity of this duct, that is the velocity of so the velocity on the center line is basically given as something like this. So this is, as you can see, this is an Eulerian description where the velocity of the water particles in the center line is given as some v1 into 1 plus x by L ex, where L you can consider to be the total length of the duct, and v1 is some constant. Constant means you can take it as some maximum velocity that may arise here, or you can just treat it as some constant. Okay, so this is given to us. So having said this, what they wish for us to evaluate is that they want us to calculate the acceleration of a particle moving along the center line using an Eulerian approach and a Lagrangian approach. Okay, this is something they wish for us to find out. I will repeat again. So there is a duct. By nature of this duct, it looks like it's a converging duct, and the velocity of the water particles in this center line is basically given to us, which is this. It's an Eulerian description, as you can see. Having said that, they want us to find the acceleration of a particle moving on through the center line using an Eulerian approach or a Lagrangian approach. So this is something that they want us to find out, and we will do that. So let us now try to solve this problem. We will try to do the first. So we'll try to do the first part, which is basically this. So we will now first try to find out the acceleration of a particle using the Eulerian approach. So let us use the Eulerian approach first. So in Eulerian approach, so we'll first write down how the acceleration looks like in Eulerian approach. So as you can see, in Eulerian approach, the acceleration is basically written as, so if you remember, it is just the temporal change of velocity plus v dot grad u. Okay, so and this is something known as the material derivative, as you guys know. So this is basically the temporal so this is the temporal term, and this is the convective term, and together the temporal term and the convective term is known as the material derivative, and this is known as, so this is known as the material derivative. And I think you guys have seen the lecture videos of this week where you understand what basically the material derivative is. So this is the material derivative. So this is how acceleration looks like in Eulerian description. And of course, I have written this in so this is written in vector form. So now if I want to write it in the x direction, so if I want to write it in the x direction, because we seek to find out the acceleration in the center line, which basically is in the x direction. So now say in X, if I write this, so this vector form simplifies to Ax, which is basically del u x, this now becomes x by del t plus ux times del ux by del x plus vx times, so if we expand the material derivative, so if we expand this term, is basically looks something like that. So it becomes vx times del ux by del y plus wx times del ux by del z. I hope this is clear. How do we get these three terms out of this term? This is rather simple. Just expand this in the Cartesian system. So now, as you can see, this is 0. Why? Because the velocity field in the center line is not a function of time, as you can see from this. So ux, as you can see, ux is nothing but v1 into 1 plus x by l, right? So from here, you can see it's not a function of time, and that's why this is 0. There is no y component velocity, that's why this is 0, and there is no z component velocity, so it is also 0. So ax simplifies as just ux times del ux by del x. Okay, and if you evaluate this, so ux is what? So ux is just v1 into 1 plus x by l, right? And del ux by del x is just v1 times l. So this is what ux into del ux by del x would look like. And of course, this is ax. Okay, so if you simplify, ax, which is basically the acceleration in Eulerian description in the x direction, is nothing but v1 square by l into 1 plus x by l. Okay, so that's it. That's the first part of the problem. They want us to evaluate the acceleration of a particle in Eulerian description. This is the acceleration of a particle in Eulerian description. So I'll write down. So this is basically acceleration of a particle in Eulerian description. Okay, I hope this is clear. If you have any doubts, please let me know. Okay, I hope this is clear to everyone. How did we did it? So I'll repeat again. So this is the definition of acceleration in Eulerian approach, where acceleration is just the material derivative of velocity, and material derivative is just the summation of the temporal term and the convective term. And of course, I have written this in vectorial notation. You can write down in x direction, in y direction, in any direction that you see. But since we are interested here in the x direction, we have written this in x direction and evaluated these terms, and we end up getting the acceleration to be something like this. Okay, the second part that they asked for, so this is the first part. In the second part, they ask us to evaluate the acceleration using the Lagrangian description. So we will use the Lagrangian approach. So now here lies the trick. So in Lagrangian approach, all we care about is how a property just changes with time. Okay, but what we know is we are just given that the velocity, that is the velocity as a function of space. So we will now try to convert this. So the idea is that from this velocity, we'll move a step back and try to evaluate the displacement as a function of time. And from the displacement, the second derivative of the displacement with time will give us the acceleration. Okay, so that is the idea. So let's proceed. So in Lagrangian frame, what we will do is so in Lagrangian frame, what we know is we know velocity. So velocity looks something like this: v1 into 1 plus. Now this x would now be x of a particle with respect to time, because in Lagrangian frame we just stick to one particle. So x would now be the x. So this x position would be the position of a particle p at any time t, and that's why I have written it as xp at a time t divided by l. Okay, I hope this is clear. So from where did we get this? We got this from the velocity description that we got. The only thing that we did is this x in Lagrangian frame would just be the position of the particle p at any time t. Because in Lagrangian frame, as I repeat, as I have said, we instead of focusing in a region, we focus on a single particle. Okay. And we know that in Lagrangian frame, velocity can be written as the rate of change of the particle p with respect to time t. Rate of change of the position of the particle xp with respect to time t. And this becomes equal to v1 into 1 plus xp, which is a function of time t by L. The idea is again to evaluate this xp. Okay. So let us now try to simplify this term. I hope this is clear to everybody what exactly we are trying to do. So this is xp as a function of time t by dt, and this becomes v1, and this becomes L, and this becomes L plus xp of t. Okay. So let's try to simplify this. So what I will do is I will try to bring this here. So this becomes xp by L plus xp, and then this becomes what? This becomes v1 by L times dt. Okay. So now what we will do is we will try to integrate this expression. We'll try to integrate this expression from 0 to xp, and time will integrate it from 0 to t. The thing is that at t equal to 0, the particle is at x equals to 0. That's what I'm trying to say. So if you integrate it, you can very easily show that this integration on the left hand side would be ln of L plus xp. Okay, and the integration on the right would be just v1 t by L. And then if you, so this varies from 0 to xp, of course, and this varies from 0 to t. You have to put the limits as well. Okay. So if you put the limits, what you can see is that this first term becomes ln of L plus xp minus ln 0, ln, so this becomes just ln of L, and this becomes v1 t by L. So it's very simple. You just go and put these limits. Just go and put these limits here. Okay. So this can be now written as, so ln of a minus ln of b is just ln of a by b. So this becomes ln of what? L plus xp by L, and this becomes p1 t by L, that as you can see. So from here, if you move the ln to the other side, okay, so what do we get? So if you move the ln to the other side, you get 1 plus xp by L is just exponent of what? Exponent of v1 t by L. This is something that you get. And xp, so what you get is xp as a function of time would just simply be what? It will be e to the power or exponent or e to the power v1 t by L minus 1, and this whole would be multiplied by L. So this is xp. So as you can see, this is the position of the particle. So we have very elegantly, as you can see, we have very elegantly converted the velocity in Eulerian frame by integrating it to the position of the particle at any time t. And as you can see, this is just a function of time. So now we are in the Lagrangian frame as we seek to like find out. Okay. So this is something that we got. But this is not what we are asked for. We are asked to evaluate the expression. Oh, sorry, the acceleration. Okay. So the acceleration in Lagrangian frame would be, so AP, acceleration of the particle in Lagrangian frame, is nothing but, it is what? It is just d2x p by dt squared. Okay. Or this can be written as dup by dt, which is basically the first derivative of the velocity or the second derivative of the displacement. And if you perform a second derivative here with respect to time, you can very easily see that apt would simply come out to be v1 squared by L e to the power v1 t by L, and that's it. That's the acceleration in Lagrangian frame. Okay, this is the acceleration in Lagrangian frame. Okay, so I'll write down here. So this is the acceleration in Lagrangian frame. Okay, I hope this is clear. So I hope this is clear. So what I did is first I evaluated how the xp, what is the position of the particle, changes with time, and then in Lagrangian system, the second derivative of acceleration with respect to time will give you the acceleration. Okay, now for a test, So for a test or a check, so what I say is now if we check two things, okay. So what I mean to say is that let us now write down what is the Eulerian acceleration that we got. So in one column, let us write down the Eulerian acceleration. And in one column, let us write down the Lagrangian acceleration. So the Eulerian acceleration, as you can see, so what is the Eulerian acceleration? So this is the Eulerian acceleration, right? I will indicate it by a box, of course. So this is the Eulerian acceleration. So the Eulerian acceleration is what? Ax. So what we got is a as a function of x is just v1 square by L. So what did we get? v1 square by L into 1 plus x by L into 1 plus x by L. Okay. And the Lagrangian acceleration we will write is as ap as a function of t, because now we are fixing it on the particle. So it becomes what? So what is it? So it is this expression. Okay. So it is v1 square by L into e to the power v1 t by L. So now let's do a check. Okay, so this is the Eulerian acceleration and this is the Lagrangian acceleration. Okay, so at x equals to 0, so what I'm saying that at x equals to 0, the Eulerian acceleration, let us now check two things. So the Eulerian acceleration at x equals to 0, which is a at x equals to 0, simply comes out to be, so if you put x equals to 0 here, this simply goes to be v1 square by L. And the Lagrangian acceleration, if we evaluate it at t equals to 0, this simply comes out to be ap at t equals to 0. So if I put t equal to 0 here, this simply comes out to be v1 square by L. Okay. So as you can see, very interestingly, at x equal to 0, in the Eulerian frame, the acceleration exactly coincide the Lagrangian acceleration at t equals to 0. And of course, this has to be right, because at the beginning of time and space, the particle will always bear the same acceleration. When it moves, then it changes according to the Lagrangian and the Eulerian description that we are trying to check. Okay, so this is a check that your calculation is correct or not, is to see whether your Eulerian acceleration at the initial space and the Lagrangian acceleration at the initial time matches your values or not. So this is the check that we can do. Okay, this is an extra that I said, but we are not asked to do the check. But anyway, we can verify our results. So the results that so the Lagrangian acceleration and the Eulerian acceleration, so whether these results are correct or not, can easily be checked if we try to evaluate the values at the initial space for the outside at the boundary, so where it started for an Eulerian approach, and the initial time for a Lagrangian approach. Okay, so yeah, so this was an important problem. So I don't think we have much time. We will simply solve some very easy problem. So these are very easy problem, and then we will call it a day for today. So first of all, uh, let's just solve one simple problem. So given that, so in this problem there is a velocity field which is given, as you can see. So whether they are asking is determine whether the flow field is incompressible or irrotational. Okay, it's a very simple problem. So I will not explain much on this, because you guys have done numerous problem on this aspect. So for incompressible, can you tell me what is the condition for incompressibility? So as I have already said, for incompressible flows, divergence of velocity divergence of velocity is 0, which means del u by del x plus del v by del y plus del w by del z. This should come out to be 0. Now let us check whether this is true or not. So what do we have? So we have from this expression, we have u, which is equal to 4x minus z. We have v, which is equals to what? It is 2z minus what? 4y, and w is just 2y minus x. Okay, so now let's evaluate what is this term. What is this term? Okay, so del u by del x. So if I now evaluate del u by del x plus del v by del y plus del w by del z. So this becomes what? So this becomes, so del u by del x is 4. del v by del y is minus 4, and del w by del z is 0. It just evaluate the derivatives of these terms with respect to x, y, and z respectively. So this means this is 0, and this is obviously equal to the right hand side, which means that of course it is the flow is incompressible. Okay, therefore the flow is incompressible. Okay, for irrotationality, can anybody tell me what is the condition for irrotational flow? Yes, exactly. Curl of v equal to 0. Yes, very nice. For irrotational flow, so this curl of velocity has to be equals to 0. Very nice. Uh, so if you now evaluate the curl, so how do you evaluate the curl? Curl is basically what? So it is I cap j cap. So you just need to evaluate the cross product. For del, it would be just del del x, del y, and del z. And for v, it would be what? It would be these terms. Okay, 4x. So it is just 4x minus z. J is what? So j is, so it is the v component is 2z minus 4y, and the w component is 2y minus 4x. So you just evaluate this. So if you evaluate, so it's very simple. If you evaluate this, what you shall get is so if you just evaluate this curl, you will get just vz. So what do you get? Del vz by del x, or vz, or whatever you write, uz or vz. So it's just del vz by del x minus del vy by del z, and this is in the x direction, minus the other terms. I mean, I think you guys are aware of what the other terms would look like. It will be del vz by del x. Okay. Oops, I don't think it's vz. Sorry, I think I miswrote this. This should be y because we are evaluating in the x. So this should be y, and this should be minus del vz by del x minus del vx by vz, and this is in the ey direction, plus this would be del vy by del x minus del vx by del y, and this would be in the z direction. Okay, just evaluate this. I will not do that now because the maths is very trivial. Just evaluate this, and if this is equals to 0, just evaluate this. If this is equals to 0, then it is irrotational, and if it is not equals to 0, of course, then this is a rotational flow that we will consider. Okay, that you can do it at your home. I'll just write it at the home. Okay, so I think that's it. This is clear. So we will end this just by solving one. Just not solving. Just we'll end this session by just highlighting or just solving an MCQ. So let's see this question. What it says is that suppose for a flow, it is possible to define a velocity potential but not the stream function. Then which of the following is true? So this is very simple. Okay, so they said that you can define a velocity potential but not the stream function. So if you cannot define a stream function, as I have said in as we have seen in multiple time, that if we define a stream function and if there exists a stream function, then inevitably, or there has to be the fact that the flow will satisfy the continuity equation, which means that the flow is incompressible. It will satisfy the incompressible part of the continuity equation, which is divergence of velocity is 0, and the flow would thus be incompressible. But if you cannot define the stream function, the flow is compressible, which means that the flow, so if you cannot define that, the flow is not necessarily incompressible. Okay, but if you are defining a velocity potential, the flow has to be irrotational. So can you tell me, like, which option has to be true in this case? So this is the last. Can you just tell me which will be the correct option here, based on your knowledge of the velocity potential in the stream function? And I have gave you the hint. So just give it a go. Like, what would be the correct option here? Yes, B. Absolutely. Very good. So B is the correct option. Very nice. So Yeah, so I think so. This means that you have understood the problem very nicely. That's a very good like response, and thank you very much. So we will stop our session here. So meanwhile, like if you have doubts, you can obviously ask. But we have solved. So what we did is we have solved some 6 problems, which are I would say these are very good problems. That I think you must have appreciated them in assignment question. So there is a question here. In assignment question, we do not require to give solution methodology, only final answer need to be. Yeah, yeah. So I believe that in the assignments, these are MCQ assignments, right? So if they are just asking to solve, so if they are MCQs, then you just need to give the MCQ answer. So and if they're asking for some numbers, let's say they're asking for some values, you need to give the values. But if they're not asking for methodology, then you don't need to give the methodology. I hope this is clear. If I remember, they are just MCQs, and or you need to answer some values. So there you just then and there you just need to type it in your keyboard. I think that's the way it goes. These assignments. Is this clear? I hope this is clear.
Yeah, yeah. Thank you.
Yeah, sure. Okay. Okay. So okay, then if you have any doubts, we can you can ask, or we shall end this session now. Meanwhile, I'll just give quick recap of what we did. So we basically solved some problems. First, we look into the Reynolds transport theorem. I think RTT is clear to you now. So the first problem involved the mass conservation. The second problem is more involved, and it basically relies in calculating the force, for which we use the RTT first for mass conservation, and then we use RTT for the momentum conservation, of course in x direction. And in y direction, I said that it's symmetric, so there is no point applying RTT. The force will anyway be 0. And then we look into a problem of stream function where the velocity field is given and we were asked to calculate the stream function. This is a good problem in the sense that we knew how to calculate psi from the given velocity field, and this is how the stream function should look like. And then I gave a quick note that when we are defining a stream function, the continuity equation is trivially satisfied. This is a very important point. It will be very helpful later on when we will move ahead in the in the next assignments. And then we look something called the Eulerian and the Lagrangian description, where we said that given a center line velocity, we first evaluated the Eulerian acceleration, then we evaluated the Lagrangian acceleration, first by evaluating what will be the position of the particle with respect to time, and then double derivative of those position with time gives us the acceleration. And then for a check, we saw that the Eulerian acceleration at x equals to 0 and the Lagrangian acceleration at t equal to 0 is equal, which has to be. And then we look into some simple questions, like if there is a velocity field, check whether it's incompressible or irrotational. And then we saw by a simple problem that if we are defining a stream function, if we cannot define a stream function, the flow is not necessarily incompressible. But if there is a velocity potential, this means that curl of v is 0. This indirectly means that if you are defining a velocity potential phi, this means that the curl of v is 0, as you have rightly pointed out. And this also means that you can now write velocity as a gradient of a scalar function phi. That's it. Which is where phi is nothing but the velocity potential. Okay. So with this, I will end this session now. Thank you very much for joining this session. Uh, the link of this session will again be uploaded, I think, in YouTube or in course website. That depends on the PMRF office and the NPTEL office. So I thank you all for joining. If you have any questions, you can ask, or I will end the meeting here.
Sir,
Yeah, yeah,
so actually, for first question, can you just try with the taking entire tank as control volume? Just
yeah, yeah.
uh,
Sure. Yeah, that we can do. Yeah, yeah,
yeah,
yeah. Actually, that I gave. Has a
yeah.
for
Hi,
you.
as a
I'll give you,
homework.
yeah. I will give you the hint anyway. So how can you give it? That's not a problem. So the thing is, if you take the tank as a control volume, okay, the point is you need to consider the air mass as well. Okay, so then there would be so the efflux term would be the same, because the efflux would be just the water efflux coming in. So this term would just be the same. Okay, and this term would anyway be equal to 0, because mass cannot change inside a control volume, inside a control mass system, that I have said. Okay, the only term that would change is this term. Okay, now the thing is, this term now need to be evaluated. So this change in volume term need to be evaluated for the water and for the air. Okay, however, if we are now applying
So
this for the yeah,
as a total, it will be zero only, right?
yeah, exactly, not as a total zero. So the thing is, this term, that is the volumetric change term, for the water there would be this term present, but for the air this term would anyway be zero, because the air mass will always be constant inside the tank. Did you understand what I'm saying? See, this is the rate of change
Okay,
of the
okay.
water mass, right? This is the rate of change of the water mass. Okay, now there will also be one term which will be dm air by dt. Okay, if you simplify this, you'll get something like dm air by dt. But since since the air is trapped inside the container, this means that the air mass cannot change with time. Okay,
Okay,
so
okay.
this means that that would anyway be going to zero, irrespective of the choice of your control volume. That's what I said. Okay,
As a overall control
yeah,
volume is constant.
yeah, exactly. Overall, the control volume is constant. Yeah,
Okay, only that air is getting compressed.
air
Yeah.
is getting compressed. Exactly.
Yeah.
However, even
Okay.
if it's getting constant, its mass would remain same. Okay,
Yeah.
since its mass would remain same, so the rate of change of air mass with respect to time would anyway be zero, even if you consider air. Okay,
Okay.
so if I want to explain it nicely, so this term is what? This is the rate of change. This is m dot of water, right? If you observe it closely, so this is the rate of change of water mass, right? Correct?
Yeah.
Because see, this is property. Okay, property per unit mass, and this rho times v is just mass, right? So it's volume times, so it's density times the volume integrated over the entire control volume. So property per unit mass multiplied by mass. So it just, so this is so this term just says that how mass, so how the water mass changes inside the control volume. Now if I apply this for air, this would be m dot water plus m dot air. Okay, however, this m dot air would be zero, since the air is just trapped inside this control volume. It cannot just move out. If
Yes.
had there been any leakage or something like this, then this would be changing. But here in this case, this m dot air is zero. So anyway, you just have to evaluate just this term only for water. That's what I'm trying to say. Okay.
Okay, okay. Thank you.
Okay. Yeah. Okay. Okay, then we will end this here. We'll end this session here. We will again meet for an interactive session in the next week, like as per the given schedule in the website. Okay, I am ending this meeting now.